Stone thrown horizontally with the velocity to the air. Okay, do this one. Thrown with velocity 8 meters per second into the air at an angle of 40 degrees to the horizontal. Here, 40 degree. Initial velocity u, make an angle of 40 degrees to the horizontal. Calculate the vertical component of velocity. Easy, This vertical velocity, I see in the assignment that you already do the similar problem, with a uy. And that uy is u times sine of the angle, sine of 40 degree, 25.7. So that is the vertical component. Question B, state the value of the vertical component of the velocity when the stone reaches its highest point. Ignore air resistance. At its highest point, the velocity at the top is 0. The balls goes like this. A parabola, to draw a parabola. When you go to the top here, the horizontal component, the velocity becomes 0. There's only the horizontal component left. Let me show you a illustration of that GeoGebra here. So we have the two vector, two colors. This is the term. Okay, the green vector is the horizontal velocity. The blue vector is the vertical velocity. Okay, and the actual velocity is this black vector, which is tangent to the path of the object. This part is a parabola because when air resistance is negligible, the equation, the final equation, when we write the equation describing the change in the height, the y coordinate with the x coordinate will be a quadratic function. With the time, that velocity changes, of course, because of the gravity reducing the velocity component, the vertical component. That component becomes smaller and smaller when going up because of the pull of gravity decelerating it. Okay, at the top, horizontal velocity remains the same. Vertical velocity becomes 0 and then falling down again. Now gravity will pull the object down, accelerating it, increasing the vertical component again downward, and this velocity keep increasing. And of course, the total velocity, black vector, always tangent to the orbit like that, and increasing with the vertical component. Okay, try finding a total of that, the velocity components. And after practicing with a few, examples, you know how to apply those formulas. Pretty good picture, too small. Okay, the black vector, the horizontal component does not change. The vertical component decreases until 0 on the top and increases again downward. I'll try another problem. Okay, the CDE here. Then 26. Use your answer to A and B to calculate the time the stone highest point. Vy, the vertical velocity, is a u initial plus gt, and I chose the positive direction upward. So the velocity here is positive, this value 25.7. Okay, and g will be negative because g is downward, minus 9.81, and multiply with the time. It's the time to go to when going to the top. At the top, this velocity is 0, so we have 0 equal to this thing, and therefore we can find this time so that the object goes to the top. Okay, 0 minus 25.7, and of course divide minus 9.81. Negative divide each other, we have positive time. 25.7 by 9.81. The time is 2.62 seconds. 2.62 seconds. That is solution question C. Question D. Calculate the horizontal component of the velocity. Similarly, u or vx, which is a times cosine of 40, 6.13 meter per second. Question D done. Question E, you answer to C and D to find horizontal distance, meaning the range. Find horizontal distance travel the stone is climbs to its highest point. We have the time here. It's the time for the object to go to the top. The total time of the flight will be twice the time going to top here, because the path of the object is symmetric. Therefore, the length going up, the length going down, the curvature, the angle is the same. So it takes 2.62 seconds for the object to go to the top, 2.62 seconds. And also the same amount of time, 2.62 seconds, to fall down on the same height on the ground. Okay? So the total time of the flight is twice the time going to top there. Let me write that on the next, page. Time of the flight is t equal to time of 2.62 seconds, which is 2.62 times 2, 24. And the range that the object flies is simply, we can write r or x max is the horizontal velocity vx multiplied with time. Vx we calculate in part D here, 6.13. 6.13 times 5.24, and we have the final result, 32.1 meter. That's it. That is the solution to this problem. Try doing one more example, and then we can stop today. The last one, 26. So from now on, I will change to the Jamboard here because it's better than the Microsoft, and you can write your solution, your answer also on this board. And at the end, yeah.
Access to edit it.
I shared already, but I probably forgot. Yeah, editor. Yeah. So yeah, after each lesson, I will export this board as a PDF file and save on the OneDrive folder that I share with you. But you can also export it as a PDF file if you want. 26. The range of a projectile is horizontal distance if traveled before it reaches the greatest range, which is if the projectile is thrown at 45 degrees to the horizontal. The ball is thrown with the initial velocity 40 meters per second. Calculate the greatest possible range when the air resistance is considered to be negligible. Okay, for this problem, I explain the formulas and why the maximum range will be achieved when the angle of the throw is 45 degrees. See the initial velocity u equal 40 meter per second, making an angle of 45 degrees with horizontal direction, 45 degrees. Of course, similarly, we can determine the two components, ux and uy. Ux is 40 times cosine of 45, and similarly, uy is also 40 times sine of 45. 45 and cosine 45 are the same value, 40 times 45 cosine. So that the two components are 28.3 meter per second. To go to the top, the Vy is 0, and Vy here is equal to Uy plus Gt. Again, I show the upward direction as positive direction, and G is downward, so G is negative 8. Again, UV here is the initial velocity U multiplied with minus U times sine theta over G. Because G is negative, so this time is positive, of course. The time of the whole flight will be twice of this one. T total is twice of T1 going to the top because it's symmetric orbit. So it is 2 times of U times sine theta over G. I just take like the value, not necessarily concerning about the negative sign. That Vx is U times cosine of the angle theta, and then I multiply with the time of the flight. 2 times of U times sine theta over G. Now I do not care about the negative sign, just take the value, just the magnitude. I ignore the negative sign for the U here.
Ignore it.
Like I just take U to be 28.3 and G is 9.8. I do not involve the negative sign on top and bottom. Just calculate the value of time. Yeah, or you can involve the negative sign, it doesn't matter. Negative sign. So if you involve negative sign for U here, remember that G is negative also. So this is the range. And have you learned the double angle sine 2x? So here sine of 2 theta multiply with U. Here you have U, here you have U, so that U square divide G. And now just take G as a normal value, positive value. Negative divide negative. So instead of writing negative, I just take the positive 9.8. Okay. So this is the formula for the range. Like this. So the maximum is 1. And therefore, when this angle is 90 degrees, and therefore theta is 45 degrees to have the maximum length, maximum range of the throw. We can illustrate that with a simulation also, projectile range here. And that is the mathematical way to prove that the range is maximum when the angle is 45 degrees. Here I can change the angle like 30 degrees, remaining the initial velocity the same, such as 12 here. Initial height here I would change to be 0, starting from the ground there. So the range here is about 0.4 something. 12.6 something, and keep increasing the angle like 45 degrees. We can see that the range changes 40 degrees, 14.4, and keep increasing until 45 degrees. The same thing. Wait, 40 and 45 the same thing. That's weird. How about 50? Change a little bit, The range here, read the value here, 14.46. So at the angle 40 degrees, the range is 14.46, 45 degrees, 68, a little bit greater. Okay, 47 smaller, 50 smaller. So The maximum range is when the angle is 45 degrees. Similarly, with this simulation, the red curve here, actually when there is the air resistance, we cannot ignore the air resistance. So in reality, an object thrown such as a tennis ball will fly like this, the red curve. Only when the air resistance is negligible, the object will fly symmetrically as a parabola in the blue curve here. Okay, we can change the surface area and everything. Air density, remove it. I want to find here the angle. 45 degrees will be the maximum range. Note the red point here only. Launch velocity. So we can see that when reducing the angle, the range is shorter, and also when increasing the angle exceeding 45, the range is maximum when the angle is 45 degrees. One more thing about the range. You have this formula. Let me write the formula again. Range L equal 2 times of u times cosine theta times u times sine theta divided by g. And therefore you see that there are sine and cosine existing at the same time in the formula. So if the angle is 30 degree, we have cosine of 30 degree and sine of 30 degree. And if you have the angle 60 degree, we have cosine of 60 degree and sine of 60 degree. And because those two angles, 30 and 60, are supplementary, right? Meaning their sum is 90. The word is supplementary, right? The sum is 90, right? So the cosine of 60 degree is equal to the sine of 30 degree, right? For 30 degree and 60 degree. Supplementary angle, or 20 degrees and 70 degree, or 25 degree and 65 degree, and so on. We can check that again. Let me change the angle to be 30 degrees here, 30 degree. The range here, 72.6. Huh? When I increase the angle here up to 50, you see it is moving until 60 again. There. The height, the top is taller, the height is greater, but the range is the same. Yeah, so that's a special thing about projectile motion. And with kind of problem, asking about the two different angles that the range is the same is a difficult problem that rarely appear. Completing this final example, calculate its greatest possible range. Now we already have the formula here for the range. Now plugging the value into this formula, we can determine the maximum range is when the angle is 45 degrees. The initial velocity that we have here is 40. Sorry, I forgot the number 2. No, did not forget. 2 times u is 40, and cosine of 45 degrees divide g, 9.81. We have the maximum range. Okay, 80 times 45 sine times 45 cosine. Oops, 45 sine times 45 cosine and divide 9. Wait, the same thing. Yeah, because we have sine of 45 is square root of 2 over 2, and cosine is square root of 2 over 2. So multiply them, we have 1/2, Yeah, 1/2 simplified with 2 here. Yeah, so we have 40 over 9.81, which is, with a calculator, 4.08 second, sorry, meter, maximum range. Correct speed, but the range is so small. That's weird. Let's check it here with the speed. Here, 40, and the angle is 45. The range is a lot here. We check the formula again. Cosine and sine u is 40. The product of sine and cosine will be 1/2. So 1/2 times 2 is 140 over g. Yeah, so basically this final value is just multiply with 40 again. Yeah, the range will be 160 meter, 163. So you see that when I got the result of 4 meter, I feel it doesn't make sense because the speed is 40 meter. That's so big speed, but distance is too short, and therefore I know there's something wrong. But the maximum range, calculate the correct possible range, condition negligible. Done. That's it for this topic about projectile motion. I'll send you the assignment later, like tomorrow. Okay, see you next time.